All right, so once again, this is kind of on you, and then whatever we don't get to, we'll just start to kind of work on and maybe try a few more. And it's all about practice. Practice makes perfect. So someone had asked about Descartes' rule of sign. So I'm just gonna do 10A. I just picked a random one. So 10A says P of X, so we're given this polynomial, is 3x to the third plus x squared minus 8x minus 12. So basically, we literally just focus on the signs. So when I say P of X, I like to just look at my signs. So that this first one's positive. Oh my God, I forgot to share it. Thank you. Always just yell at me. I always set it up and then I forget to share. One of these days, I'll remember. And then by the time I did, I was a little full in person. But there you go. Okay. Okay, so I'm just focusing on my signs. This first term is positive. The second term is positive. The third term is negative. And the fourth term is negative. So literally, I don't even care about the numbers, to tell you the truth. I really am just focusing on the signs. And I'm looking for sign changes. So from positive to positive, that doesn't change, okay? But from a positive to negative, there's one change there. And then negative, negative, there's no change. So one change means that there is one positive real root. Okay? So when I do P of X, that means it's positive, right? We haven't changed anything. However many changes there are is however many, or possibility, number of roots. You can also subtract 2, but obviously if we subtract 2, we'll get a negative. So we don't have to do that for that one. But let's say if this was 5, you would say 5 or 3 or 1. In our case, we can just have 1. We can't have anything else. But it also asks, what are the possible negative real roots? Okay, so I'm going to do P of negative X. I'm going to do this one out, but after this, I do like to try to kind of just do it in my head, just so I don't have to write it out every time. But here's what I'm doing. I'm thinking to myself, if I take this original polynomial, and instead of X, I plug in a negative X, you really just want to think, what's that going to do to my signs? Okay, so think about cubing a negative. A negative times a negative times a negative is a negative, right? Because 2 negatives make a positive, but 3 would make a negative. So if I have a negative cube, that's a negative, times 3 would still be just a negative, okay? If I square something that's negative, that would make a positive, and we had a plus there, so that's positive, okay? If I just have a negative, I just look and say, oh, well, it's connected with a negative here, and 2 negatives we know make a positive, and then the last number is just negative. So that one you have to kind of think a little bit. If I have a negative and I plug it in, what does cubing do to it, or squaring do to it, or how are numbers connected to it? Would they stay positive? And we're looking for sign changes. Excuse me. We have one sign change here. This is the same. We have another sign change here, which means we had 2 changes. So we could say there are 2, or you can always subtract by an even number, so you can always subtract by 2, or 0 negative real roots. I know when we did that little packet, we talked about the imaginary ones. It doesn't ask about the imaginary ones, so you don't really care about it, I'm going to be honest. You really are only going to care about the positive or negative. So we know there's one positive. So if there's 2 negative, once again, you don't really care about the imaginary, or there could be no negative. But we know there's 3 roots total, so we can kind of get that. But for those ones, that's all you have to do. So don't worry about the imaginary roots. You don't need to make a little chart like we did in that thing. I'm going to be honest, I've never even done that chart before that little worksheet. I think it was just a way to kind of organize it. I just go through, look at my signs, find my changes, and then whatever the changes there are, that's how many roots there are for that case. But just make sure if you have something greater than 1, you can take it and you would subtract 2 off of it every time as well. So you have a few different options. But that's Descartes' rule of signs. I always want to say law of signs, because in trig right now, I'm teaching something called law of signs. But It's the rule of signs. Literally just look at the signs. How many changes are there? That is how many possible positive real roots there are. So that's what you would do for 10 A, B, C, D. So then there was a question on 11. We're going to pick on H. So we look at 11H and we say, okay, we have this big long polynomial. I'm going to do the rational root theorem to figure out like what are my possible roots. Because once again, we're kind of going in blind. Like I don't really know what the roots are of it. So let's start with that and then we'll see what happens as we keep going here. Excuse me. Use 11H. What do we got? We have a nice polynomial. X to the fourth plus 4x to the third plus 6x squared plus 4x plus 1. Okay. And I just start going through my motions here. The factors of the constant, which remember the constant is just the last term right there. I'm loving it, plus or minus 1. The best possible thing I can see on this problem. The factors of the leading coefficient. So the first coefficient here, oh, beautiful, plus or minus 1. Loving life, because my possible rational roots, if I take constant over coefficient, it's just plus or minus 1. Oh, loving life. I grabbed my calculator to check. So let's plug 1 in here just to check. I mean, we don't have that many options, but you can't just randomly pick something. So if I do 1 to the fourth plus 4 times 1 to the third plus 6 times 1 squared plus 4 times 1 plus 1. Is 1 not a root? Sometimes I just plug things in wrong. Huh?
It's not.
It's not. Oh, okay. That was surprising.
Yeah, that's why I was confused.
I was going to go with it, but okay, let's check negative 1 then. Sometimes I just like hope things magically happen, but obviously that didn't happen in my life. Okay, so negative 1 is a root. When I do p of negative 1, it does come out to 0, meaning negative 1 is a root. So we can start with at least one root and go from there. So we're going to do a good old synthetic division. So we would have 1, 4, 6, 4, 1. Cha, cha, cha. Negative 1 is 3, is negative 3 is 3, is negative 3 is 1, is negative 1 is 0. So I'm left with x to the third plus 3x squared plus 3x plus 1. All right. So sorry to tell you, even though this one's not that bad, if you don't know where to go from there, what could we do? The rational root theorem again. There you go. But it's not. This one's nice. So because you have 1 and 1 again. So I'm just going to say the possible rational roots are plus or minus 1. Hey, hint. If 1 is not a root here, then 1 is not a root here. What is the root of this? It's negative 1. That's why you couldn't really tell from before, because you're like, I only have 2 options and only 1 works. But you can have a root occur more than once, absolutely. But if you're ever stuck and you really don't know what's going on, you can always do rational root theorem again. Thankfully, those were nice numbers. So I'm just seeing how much room I have over here. Not a lot, so let me move you guys over. Let's come for a little ride. Come on, guys. There we go. There we go. So I'm going to take this and divide by negative 1. 1 is negative 1 is 2 is negative 2 is 1. negative 1 is 0. So I end up with x squared plus 2x plus 1 equals 0. Why am I confused right now? 1 times 1, but 1 plus 1. Wait, does that work? Yeah? Okay.
Yeah.
I'm just second guessing myself then. Oh my gosh, look at it. Look at all these roots, and they're all negative 1. So x to the 4th plus blah, 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 blah has 4 roots. All 4 roots are negative 1. Negative 1, negative 1, negative 1, negative 1. There you go. That one's just kind of funky. Oh, that's so good. Yeah, I really need to like clean this bad boy up. It is very hard to read. Wait, did I do that right? All right, so that was a little funky because they all ended up being negative 1. So if you like, once you did it once, you're like, I don't know what the other ones are. That's just because that one keeps repeating. But once again, if you kind of get stuck with another polynomial, and like, I don't know what the roots of this are. If you don't know the roots to something, you can always fall back on that good old rational root theorem, and that will do the job for you. But once again, if you see something's factorable, feel free to factor it, obviously. If you see other things kind of popping up that will be helpful to you, do those. All right, let's pick one. I feel like everything we've had have been like kind of like nice real numbers. Let's pick one where we're gonna have like an imaginary answer. So let me kind of scroll through. I'm just looking at some different problems. I just want to find something with some.
Yes, is all
I'm gonna be honest, I might not make you do all of these problems. Just when you do that rational root theorem, it takes forever. All right, let's pick, I'm just gonna go randomly to number, where was I on? 12. Let's do 12A. Okay, I'm gonna go to 12A. I'm sorry, I kind of just gave a hint. So all of these answers will not be real. We'll have some imaginary answers, and that's okay, right? So when we have roots, we can have real, we can have imaginary, we can have anything under the sun here. But we're gonna do 12. Okay, so I just don't want to start too far over for the peeps at home. And we say x to the 4th plus 4x cubed plus 7x squared plus 16x plus 12 equals 0. All right, so I'm not hating this one too much. When I see those big numbers, I'm like, ooh, 12 I can deal with. So I go through, okay, I have no clue what's going on, so let's just start rational root theorem. Constant is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and maybe I do hate 12, plus or minus 12. It's more than I wanted, but that's life. At least the coefficient, the leading coefficient, if I can talk, is just plus or minus 1. So to find my possible rational roots, where just everything would be divided by 1. So it's basically that same list, but I'll rewrite it just to be more formal. Okay, so we have our nice list. We're gonna start kind of checking some because once again, we kind of really go into these blind, not knowing what's gonna work. Excuse me. So I just throw it in my calculator and watch something magical happen, hopefully. So 1, excuse me, I plugged in negative 1. 1 to the 4th, oh, this is a long one, plus 4 times 1 to the 3rd, plus 7 times 1 squared, plus 16 times 1 plus 12. Okay, P of 1 does not work. Here, I can do these quick. So I just kind of grab it. Let's try 2. Oh, okay. So here's my hint. Ready? Because this is actually going to save me a lot of work. This is where, like, I didn't technically ask you, using Descartes' rule of signs, how many of each type there are. But this is something to look for because it will actually save you work. See how this is plus, 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 right? There are no changes. So if these are all pluses, 1, 2, 3, 4, 1, 2, 3, 4, no changes means that there are no positive real roots. So I don't even have to check the positive ones. So that's where that rule of signs, I always want to call it the law of signs. That's where that rule of signs might come in helpful, especially if you see a lot of options. Just do a quick check. There's no changes, and that's, my positive polynomial. I'm not even going to check my positive. Because why? Because I know it's not a thing. So that's something maybe you want to start looking out for. If you want to check them all, go for it. But I was just thinking like, oh, I don't want to check all those. If I had to, I would. But why do more work than you have to, right, guys? So let's try a negative root. So I'm throwing -1 in, which is kind of annoying because I have to like insert my negative sign. But you got to do what you got to do. Oh, delightful. So I just saved myself a lot of work because p of -1 is 0. I don't know why, I just clicked in my head, like, wait a second, those are all positive. If those are all positive, there's no sign changes. If there's no sign changes, then that means there's no positive real root. So why even check the positives? Okay, so, thank goodness. Okay, I saved myself some work. And now let's do the actual synthetic division. Remember one thing with synthetic division, since we're saying this is a root, your remainder should be 0. So just like little things to be on the lookout for. So this is 1, that's -1 is 3, is -3 is 4, is -4 is 12, is -12 is 0. Okay, so we end up with just x to the third plus 3x squared plus 4x plus 12. Hey guys, I think that you can do factor by grouping, right? So I always do a quick check because technically you can do rational root theorem again. I mean, if you want to, go for it. Happy for you. But if you see something's factorable, just factor it. Why not? So I just do a quick check. I kind of make my groups in my head, and I said if I took out the GCF of each of these, remember the big thing with factor by grouping is you need, once you take your GCF out, you need those to match. So if you see they're going to match and you can kind of do it quick, do that. Like, why do rational root theorem all over again if you don't have to? That gives me x squared plus 4, x plus 3. And I need to find my roots from here. So as I'm just going to kind of write my answer over here. So my roots are at -1. 3 is pretty easy. I can see that right away. Excuse me, -3. Whew, can't have a negative. I don't have any positive roots. I can have it. And then I have that x squared plus 4. So I do need to solve that. I set it equal to 0. I subtract the 4. And then I take the square root. And that will give me plus or minus 2i, right? So you could write 2i, -2i, whatever you want to write, plus or minus. But we know that if this is a 4th degree polynomial, we should have 4 roots. Excuse me. We know we did kind of Descartes' rule of signs quickly just to kind of show us, oh, wait a second, we can save ourselves some work. So none of those are positive real roots. We ended up with 2 negative real roots and then 2 complex roots. But those complex can kind of pop up here and there. They're still a root. It's just remember when you graph it, you don't really see it on the graph. It kind of just changes some direction. So that was a good one. I wanted to just like bring in some other stuff. Especially for ones you're like, oh, if I have to do all that, maybe like using Descartes' Rule of signs might save you a little time for some of that stuff. And go from there.
That's the lot.
Okay, I was gonna have you guys finish this, I'm not gonna. It's just like, how many times can you do rational root theorem? We'll pick a few to do. For homework, but then we'll.
You study for 1 more hour, you usually say you don't want to just.
So right now, before we kind of look at anything else, so have a few extra minutes to try a few other things. Are there any other specific questions that people want to go over? We are gonna go over 9E together on Monday. It kind of directly relates to what we're doing on Monday. We'll call them complex zeros. But was there anything else as people were trying them or doing something or whatever, that people had questions? Give me a second.
Intercept, so if the slope is 3 plus intercept.
Oh,
50.
what would that look like on the graph? I don't know if this one you're talking about, but if you're talking about this one on the graph, you would see the zeros at -1, -3. The imaginary ones you do not see. It really just affects the turning points. So it just looks weird. So there would just be 2 turning points somewhere on the graph that you wouldn't even know the exact spot of them. But that's what happens when you have imaginaries. So you see the real ones, the imaginary kind of just affects where things turn. Just a heads up. Okay, so now I'm just running. All right. I don't want to torture you guys, but let's see. I'm just seeing what other questions I have.
Number 3, what are the units of the slope? The units of the
Always
slope, always units y, units x.
Rational roots, find the roots,
So,
find more roots,
we use
find other roots.
Point per
That one's easy. Okay, so it's just a whole bunch of rational roots.
hour.
Let me find which ones are gonna be the easiest for you. Give me 1 second, I'm just analyzing here. I'm just gonna give you random ones. You ready? I was gonna tell you to finish the rest of this packet. I can't torture you like that on a Friday, guys. But I'll give you the rest of the class, which is 15 minutes. And can you try these ones? And then we can look at the Monday. I'll put the answers up to all the other ones as well, but unless you really want to do them. I feel like when you do the rational root theorem, it's not torture, but it's just a long problem to have to do like 28,000 of. So, can you guys try? We already did that one, so that's fine. Can you try? We'll do 13, 14. Those ones aren't bad. Those are just kind of like quick ones. And I'm just gonna pick maybe like a few random ones. So let's do, use rational root theorem. How about 20? We'll pick one from the back of that page. Let's do one with a coefficient other than, a leading coefficient other than 1. Why don't you try 24? You guys already did 31 to 36. Don't care. There's already one like that. Sorry, I'm just trying to find a different one. Let's do 39. And 40. So reassessing, because I originally was going to say just finish those. I can't do that over the weekend, guys. I'll enjoy some Papagino's pizza instead, okay? So I just picked a few. So 13, 14 are kind of like, there are no problems there. One of them you just have to think, really. There's no lot of work. A few rational root ones. I threw one, I feel like a lot of the ones we've been doing have had a leading coefficient of 1. So I did throw 1 or 2 on with just different leading coefficients, just so you kind of get used to that. You'll have some fractions, and that's okay. But just to remind you, not everything is a nice, beautiful integer. Sometimes we have fractions. That's what rational means. Rational means you can write something as a fraction. So that's that. And then some like the end problems. You guys can try this one. So hopefully that's a little bit more doable. That's our main goal. We